For UPSC Chemistry Optional Paper I, Section A, Inorganic Chemistry, the F-block elements, lanthanides and actinides, carry consistent weightage. Questions in this chapter generally test fundamental inorganic principles, electronic configurations, oxidation states, lanthanide contraction, spectral, magnetic behavior, and separation techniques. Below is a breakdown of the core concepts, trends, mechanisms, and key mathematical, descriptive expressions required for this topic. 1. Electronic configuration and oxidation states. Lanthanides, 4F series, text, Ce, 2, text, Lu. General configuration, text, Z. 4F 1 to 14, 5D 0 to 1, 6 is squared. Primary oxidation state, +3 is universally the most stable state due to the balance between ionization enthalpies and hydration, lattice energies. Variable states, +2 and +4, occur primarily when attaining empty, F0, half-filled, F7, or fully filled, F14, subshells, +4 state, text, Ce, 4 plus, 4F0, strong oxidizing agent, text, Tb, 4 plus, 4F7. +2 state, text, Eu, 2 plus, 4F7, strong reducing agent, text, Yb, 2 plus, 4F14. Actinides, 5F series, text, Th, 2, text, Lr. General configuration, text, Rn, 5F 1 to 14, 6D 0 to 1, 7 squared. Oxidation behavior, exhibit a wider range of oxidation states, up to +7 in text, Np, and text, Pu, compared to lanthanides. Why? The energy gap between 5F, 6D, and 7's orbitals is significantly smaller than that between 4F, 5D, and 6's, allowing 5F electrons to participate readily in bonding. 2. Lanthanide and actinide contraction. Lanthanide contraction. As atomic number increases across the 4F series, there is a steady decrease in ionic radii of text, M, 3 plus, ions. Because F orbitals have diffuse shapes, they exert poor shielding on outer electrons. The increasing effective nuclear charge, Z underscore, text, F, pulls the outer 5's, 5D, and 6's shells inward. Major consequences. Identical radii of 4D and 5D elements, pairs like text, ZR, text, HF, text, NB, text, Ta, and text, Mo, text, W, have nearly identical ionic radii, making their chemical separation difficult. Basicity trend. Basicity of hydroxides decreases from text, Le, O, underscore 3 to text, Lu, O, underscore 3. Text, Le, O, underscore 3 is the most basic because larger ionic radius implies weaker covalent character in the text, MO, bond. Complexation tendency. Increases across the series as ionic radius decreases, increasing charge density, frac, Z, R. Actinide contraction. Analogous to lanthanide contraction, but stronger per element because 5F orbitals shield even less effectively than 4F orbitals. 3. Spectral and magnetic properties. Absorption spectra and FF transitions. Sharpness. Unlike DD absorption bands in transition metals, which are broad due to crystal field interactions with ligands, FF absorption bands are extremely sharp, line-like. Reason. 4F orbitals are deeply buried beneath the outer 5 squared 5p 6 subshells, shielded, rendering them largely immune to external ligand field effects. Laporte selection rule. FF transitions are Laporte forbidden. Delta L equals PM1 rule. However, weak intensity arises via vibronic coupling, mixing with opposite parity states, e.g., 5D. Magnetic properties. Unlike 3D transition metal complexes where orbital magnetic moment is quenched by the ligand field, mu underscore text spin only equals SQRT n plus 2, lanthanides show strong spin-orbit coupling. The total angular momentum quantum number J must be used, where the Landé G factor is ground state determination, Hund's rule, for less than half-filled subshells, F(1) to F(6), J equals vert, L, S, vert. For more than half-filled subshells, F(8) to F(13), J equals L plus S. Key exception, text, SM, 3+, and text, EU, 3+. Their ground state J level is close in energy to excited J levels. Thermal energy, KT, populates these higher levels at room temperature, causing experimental magnetic moments to deviate from the ground state formula. 4. Separation techniques. Separating individual lanthanides is challenging due to their nearly identical +3 ionic radii and similar chemical behavior. Modern separation relies on small differences in hydrated ionic radius and complex stability. A. Ion exchange chromatography. A mixture of text, lane, 3+, ions is loaded onto a cation exchange resin bed, text, resin H, plus or text, resin NH, _4, An eluting agent containing a complexing ligand like EDTA or alpha-hydroxydisbutyrate is passed through. Principle: smaller, text, lane, 3+, ions, e.g., text, Lu, 3+, have higher charge density, form more stable complexes with EDTA, and are eluted first. Larger ions, e.g., text, La, 3+, elute last. B. Solvent extraction, liquid-liquid extraction, uses organic extractants such as tributyl phosphate, TBP, in an organic solvent, text, kerosene, against an aqueous nitric acid phase. Principle: text, lane, 3+, forms neutral adducts like text, lane, no, _3, text, _3, CDOT3, text, TBP. Extractability into the organic phase increases with atomic number due to increasing charge density. 5. Lanthanides versus actinides. Core comparison. Feature: lanthanides, 4F, actinides, 5F. Orbital shielding 4F is deeply buried, shielded by 5s, 5p. 5F is less deeply buried, extends further outward. Oxidation states: mainly +3. Few instances of +2, +4. Variable: +3, +4, +5, +6, +7. Due to low 5F, text, 6d energy gap. Complexation: weak tendency. Forms complexes mostly with chelating oxygen ligands, EDTA, beta diatones. Higher tendency to form complexes due to higher charge density and available orbitals. Oxocations. Do not form oxocations. Commonly form oxocations like text, UO, _2, 2+, text, NPO, _2, text, PUO, *2, 2+. Radioactivity. Non-radioactive, except promethium, text, PM. All are radioactive. Sample practice question for paper I. Q. A. Calculate the theoretical magnetic moment, mu*, text, F, in Bm, for text, Nd, 3+, Z equals 60, in its ground state using the Landé formula. B. Explain why text, L, O, _3 is more basic than text, Lu, O, _3. How would you like to continue? Show the step-by-step mathematical solution to the sample question. Provide past 10 years UPSC paper I trend analysis for F-block elements.